Hello, good morning. So today I'm actually gonna go back to some of the more implementation issues and use this chance to maybe even ask some questions and do some demos. We were talking about 8051 for a while, and so we're gonna look at some more assembly code because understanding assembly is crucial to understanding how threads work. And one of our major projects is really to do threads package. And we're doing not only cooperative threads, but also preemptive threads. And you saw earlier with this example of interrupt version of UR to LED. Understanding how interrupts work is crucial to preemptive scheduling because that is the only way hardware can get control back from user program. Otherwise, user program just keeps running, right? So any interrupt can steal control back because whatever the user program is doing, it doesn't even know an interrupt comes in. The interrupt just happens, right? You set it up and then once in a while, interrupt comes and the user program doesn't even know it gets interrupted. Why? Because the hardware is safe state. In fact, ISR has to save some state too. And then after it finishes certain things, it restores the state, comes back, and the user program is exactly the way it's left out. It doesn't even know, other than perhaps the time has elapsed. Or maybe some what's called volatile variables may have changed. So that's the important concept. Some of you may still have trouble with the concept of interrupt because it's not exactly natural, but really you gotta understand how interrupts work. So these are examples to help you understand interrupt, right? So how this one works is you set up a serial interrupt as opposed to polling, right? And then what it does is it's not, I mean, it does the same check as what a polling does. So this one is, you remember this one, you type on the UART, send a character, and then have it print out that digit on the LED, right? So it does have to check whether it's TX or RX because they share the same routine. So that's why in this case, it checks if TI, that's the interrupt flag or the ready flag for transmit. But we're not really using transmit in this particular example. We're just receiving. So still, if it's TI, we want to clear it. Otherwise, it keeps interrupting us, right? And then RI, that's receive interrupt, so to speak. I mean, even though if you don't set up interrupt polling, it still pull the same flag, right? So by checking to see if it's equal to 1, if it's 1, that means there's a valid byte to be read in SBUF, right? So yes, you do that check, but in the ISR, you don't do a for loop or while loop or whatever loop inside the ISR, because that's defeating the purpose of doing interrupt in the first place, right? So don't take your polling loop and stick it in the ISR. No, that doesn't make any sense. The ISR is there because hardware does that checking for you, essentially the polling. And then if it sees the bit change, it doesn't clear the bit, at least not UART, and then jumps to this interrupt service routine for you, okay? So that's what that routine looks like. You could write this in C if you really want to, but of course you have to make sure you don't accidentally link in these other functions that SDCC assumes that exist for clearing up your RAM bits. So here, if you want to declare a serial ISR, you do this and double underscore interrupt and then the number in the parentheses. So here it's if, right? It's not while. And then, well, this is not exactly equivalent, but this is really just a template for it, right? So if TI is is set, that means transmit ready, we really don't need to do much other than clearing it, right? And then the receive part would just follow this TI part. So if receive, so it's just linear code down. Don't do a while loop. Okay, so this I think we went over this. Just a quick recap since it's been a while. Now here, so if TI gets 0, if RI then that means there's valid byte to be read. So sbuff, you read it, put it in Rx data. Presumably this is a global variable. And then Ri clear it, and then display LED gets whatever value you read minus 48. Okay. Now you can say, okay, let me just stick a sbuff in here instead of Rx data minus 48. Is that going to work? Most likely, you can just try it because that's just a move out of it. And what the compiler most likely does is it has to compute the sbuff and then minus 48. So it has to move it probably into an accumulator and then do an add of minus 48, right? And then back in the accumulator and then do the LED display, right? So now the difference with this interrupt 4, as you remember, is that because an interrupt returns differently from a regular function. Regular function will use RET to return. An interrupt service routine uses RETI. And so have it generate the code, take a look to see if it really uses RETI. Okay. And then here, well, we could technically call a different function here. I'll call LED display LED. We've seen that before. But is that a good idea? Well, again, it's up to your judgment, and you need to know what the consequences of calling it the display LED from here. Because there is a difference between what's called a function call versus a subroutine call. When we do an lcall instruction in 8051 or in most languages, it's what's called a subroutine call because that is an ISA supported concept. When you do it in a high-level language like C, and you just do the name LED, whatever, display LED paren, that's a function call. Well, a function call is a fancy version of subroutine call. So yes, for the control transfer and return, it uses the native instructions. But a function call does a lot more. What? Well, passing parameters, setting up your local variables, return values, right? The function is actually a higher level concept than the subroutine. And those things are not free. Those things take up resources as well. So you got to know what kind of resources and do you want to pay that price inside your service routine, okay? So one of the first things it has to do is what's called saving registers and restoring. That's all all implementations of functions have to save and restore registers. Why? Because, I mean, if you ever taken a compiler course or if you ever taken a look at generated compiler code, you know how compilers work. It's that you have some expression you want to evaluate and you take like A plus B minus C and all those things. And then it's, but those things have to be broken down into simpler instructions because it knows how to do add, subtract, multiply, divide, and also shift maybe. And those have to be mapped to some, right? So your A plus B minus C, those have to be broken down into machine instructions. And that means it needs to use some temporary variables, such as R0, R1, R2 to R7, accumulator, maybe sometimes even the B register, sometimes DPTR, right? We've tried to craft some code like that. So those hold temporary values, right? And when you make a function call to you, it's okay, you're making a function call. Well, what happens a lot is it transfers control to a separate routine. And presumably that routine is called from different places, right? And that means it better present that illusion that by the time it returns to whoever calling you, those other registers, if it ever has to use those same registers, will be saved and restored, just like an interrupt would have to save and restore those registers, right? So that the caller can continue using whichever register they use to store their temporary values, to store their local variables. So that might seem like, okay, what's the big deal? Well, it could be a big deal. Then we can take a look at some generated code to find out. And this is especially a big deal inside an ISR. Why? Because ISR just already saved a bunch of registers to present that illusion to the interrupted program. Okay, I'm going to save and restore so that you don't even know any registers got trashed in the meantime, because it does need to use some of those. Now, if that ISR calls some other function, guess what? Either that ISR or that called function has to save more registers again. It's like, hey, I just saved register. Why do I have to save again? Right? So you end up spending a lot of time saving, restoring these registers. And that's why, for a long time, especially embedded system programmers don't trust compilers, because they think compilers do a stupid job saving, restoring, spending all the cost saving and restoring registers just to something really simple, right? And it's not until the past decade or two they got a lot better. So then, okay, fine, we'll start using compilers more. Otherwise, a lot of code for embedded used to be done all in assembly, just because it's quite a bit of cost. But that, you still need to know that, because still, if you write this in the compiler, it may or may not be smart enough, because ISR usually is used in something timing critical. You don't want to spend a lot of time in ISR, and you want to be very frugal in your ISR. So still, ISR code could still be handcrafted, even for general purpose systems. Anyway, so let's take a look at the generated code, okay? That interrupt led.lst, or you can look at ASM. So it shows, I mean, yours might be a little different, but this is what mine looks like. So what does it do? It pushes bits, pushes ACC, pushes B, pushes DPL, DPH, pushes, what's 0 plus 7? That's the absolute address for register 7. Because R0 through R7 get mapped to direct address 0 to 7. So 7, 6, 5, 4, 3, 2, 1, and push PSW. And that's just on entry to the ISR, okay? It pushes those registers. I said, I didn't write this code. Well, the fact that you use a high-level language construct in the form of a function means compiler does this work just so that it can implement the function abstraction, okay? This is the cost. So a compiler, just to be on safe side, yes, it would have to push and pop those same registers so that it can safely use those registers, okay? So, and then you keep going. Well, okay, now we're getting into the body of the code, because your listing will show also what your C code looks like. So it does the move of constant or immediate 0 into PSW if Ti equals not, well, if it's true, right, it means not 0, that means bit is set, then do this. So JBC, Ti gets 0, and then, so that means jump is bit is clear. In other words, in C, you think if true, I do this. In assembly, you think if it's false, I jump out of it, right? So that's JBC. So jump to this 00113 $, that's a label. That's a local label, okay? So what's that? So that's this label here. So that skips the part for the. So I actually took out some stuff. Anyway, then there is if Ri, then jump if not bit, right? So, oh sorry, no, JBC means jump and clear bit, right? So if the Ti is set, then it clears Ti and then does a jump. So that was what that was supposed to be. Yeah. And JMB is jump but not bit. Okay. So if Ri then not bit, if Ri is false, then skip out of this. Right. So it jumps to label, which is at the end. Now it does a SBUF read. So as you can see, it's moved from SBUF into RX data. That's another direct address. And then Ri is cleared, so it's clear Ri. And then display, that's to call that function. Well, what do? Well, you load the old value into A, or the current value or Rx data into A, and then does the add of what's hex D0? Well, hex D0 is really just minus 48, right? Remember 2's complement representation? You should all be very comfortable with this. I shouldn't need to review this, right? So that's you basically flip all the bits and then add a 1. That's how you get the negative version of it in 2's complement representation. Then move so the result, move to DPL. Why DPL? Because in SDCC, you pass parameters. If it's a single byte, you pass in DPL. If it's 2 single byte parameters, pass in DPL and DPH. Or if it's a 2 byte parameter, passes in DPTR, which is concatenation between DPL and DPH. And that's so that it can make the call to display LED, okay? And then after that, returns back, pops PSW, pops registers 0, 1, 2, 3, 4, 5, 6, 7, pops DPH, pops DPL, pops B, pops ACC, pops bits, before it does the RETI. It's like, what? Spend way more code just on pushing and popping all these registers compared to the little code for me, right? And then that doesn't even count the display LED code, right? And then, so that seems like not such a good idea, does it? Right? So, so of course, no. That could also mean SDCC is not doing a great job. But that's in general, that's kind of what you have to assume. You can't assume your compiler to be that smart compared to when you craft the code. So if you have to craft the code by hand, then you then can decide which ones actually get affected and which ones don't need to be saved and restored. Okay. Well, so, okay, this is outside the scope of this course. You can take a compiler course to learn about this. There's convention of what's called caller save versus callee save. So caller save, they basically saves all of those that it uses once preserved. And callee save means it saves those that it will use. So, and then when, so it's an agreement you have to make between the caller and callee. And so that is a convention that has to be consistent. So there's no one or the other way to do it. And then there's, of course, trade-offs there. Sometimes, I mean, in one way or the other, you always may have additional registers that don't need saving, but you save anyway and restoring them. So compilers, unless you inline everything, but then that increases code size. So there's no just one way to do things. Okay, so so that is for week 3, and then I'm gonna quickly bring up week 4 on. So we did go over. This is not the one. Oh yeah. Oh, okay. Well, actually, I didn't. This is part 2. Oh, yeah. I wanted to show you some demos I didn't have much time to do last week, but I think, oh here. So did I show you demo for shared memory? Probably not, right? Okay. I did tell you the place to change, right? So the book actually included a different, like shm.h, that's not going to compile. But if you do change this to system mman.h, then it should compile. Anyway, so we'll switch to this for a little bit, and then I'll go back to SDCC, just so that you get a chance to see things at different levels. Okay, so this, okay, so 8051. Or did you want to see 8051, that how that interrupt works? It actually worked. But maybe later, I think some of you guys had some problems with bugs or you make some changes to it. My code works, and then you make some changes and somehow it didn't work. I could maybe debug that in front of class in a little bit. But anyway, so I wanted to show some code. So because there's some code you may not have. Okay, C code, right? So share memory, and so there is producer and consumer, and then separately. So you can do CC or GCC, share memory consumer.c. If you do this, it's gonna make a dot out. So that means, oh, well, did I? Okay, so you can do minus LRT. So if you do for, what? Did I? Oh, okay. My setup changed. Okay. Okay. Now let's try it again. Oh, minus LRT is only for Linux. Did I do that? Oh, it's Xcode. Sorry. Xcode. Just one word. Good. To agree to all this. Sorry. Yes. Agree. Okay. One more time. So if you don't do the minus O, then it just names it a dot out by default. Okay, that compiles successfully. A dot out, I can rename it. A dot out to be SHM consumer, and then or I can do CC or GCC as producer minus O as this SHM producer. Is that too small? Maybe bigger. Okay. And then, so what do I do? So remember this code? That's from the book. Okay, so let me take a show you real quick. More producer.c. So it really sets up the shared memory producer using essentially a name, and that name is through the file system. That's how they can find each other. Otherwise, you don't have a way. And then do the mapping, right? Remember this one? Okay, so this is straight from the book. And then I can use I do SHM producer, and then SHM consumer, and then just have them run. Hello world. Okay. So what the ampersand does is it's to start a process from the shell in the background, so it keeps running. Okay, so I don't have to wait until it finishes before I can type the next command, and then it has a job number 1, and then I then do the consumer also, and so I started both, and then it shows me it's done. Okay, now let me do a stream producer. If I do this, okay, well actually it's consumer. So it also runs it with a shared memory, but then it's the consumer that clears it up. So even though this program looks like it finishes, it actually leaves a shared memory and the consumer can find it. So that's kind of a strange concept, but then that's how this particular API works. Okay, and now what I can do is this version, snpc.c. Okay, so this version basically uses a fork, you see here, right? It uses fork to start a producer and a consumer, so I don't have to type separate commands to do that. So I can do cc, the last file, minus O, just shmpc, okay, and then shmpc. Okay, so this is a slightly different one, but what do? Well, they have that buffer, right? Except I map the buffer to share memory, so it says make and then consume. So as you can see, they are not synchronized because there's a buffer in between. So one producer keeps producing until it fills up the buffer, can't do much, so it just spins, and guess what? Context switches into the other one, and then The other one, when it gets the time, it consumes until it's empty or gets context switched out. So that's why they're not in sync. But that's okay. Let's take a closer look at this one. So it does. Oh, sorry. Sorry, my setup is a little strange today. Okay. Yeah, that looks a little better. So I think I explained this in lecture 2, but this is a quick review. Basically, you define a struct that then is overlaid on top of the shared memory, right? So you basically take a pointer to this type, whatever shared memory is typecasted to this type, okay, or the pointer to this type. Then you can do the arrow notation. So when you do the these producer, right? Remember that right, you always use PTR arrow in, and then that means the dereference the struct pointer and then get access field, the MP LP. That's straight from here, MP LP. So you're actually referencing the fields in that, right? The shared buffer. And now this one thing that's done a little differently with the book example is that because you remember the one producer consumer, one modifies LP, one modifies NP. Whereas in the book example, the consumer only reads but never updates anything, right? So here, what that means is producer does the create and rewrite, and the consumer part, you do open for rewrite, not just read only, all right? So this way, it can also make changes. If you don't do the rewrite and you try to make changes to that shared memory, a number of things could happen. It could either do a signal and it's like a kill interrupt. And now you a segmentation fault or access violation or something, depending on the system. Or worse, it could just fail silently. It doesn't tell you anything and no data has changed. And you sit there, what? not knowing what's going on, okay? So that's what could happen. That's what happened to me. My system didn't tell me anything. I just copied the code from book, changed it, and say, hey, how come it's not doing anything, right? One side just produces and it gets stuck. The other side, it just keeps, it couldn't update because it couldn't move the pointer, so it's always stuck in there, right? So that's one of the things you got to know. So it's not easy debugging system programs, but that just shows the importance of knowing exactly what's going on. You have to know very well exactly what is happening. You can't just assume, oh, that code works, I take it and make small change and I don't have to understand most of it. No, that's never going to happen. You have to know exactly what every line does and every parameter, okay? So yeah, that's one of the things, right? So so when the consumer opens it, has to do the rewrite in order to update that FIFO pointer, right? And that way, the other side can see it and can test it, right? So, and then you notice when it's blocking, this is essentially blocking, right? Producer will block when the buffer is full. And I only put yield in comment. It's an infinite loop here. How does it get out of infinite loop? Well, because the shared memory content can change, right? Anytime you do PTR and then arrow something, you're accessing shared memory. So you're relying on the shared memory state to be updated by whoever else is sharing memory so that you can get out of the loop. This also assumes you have a preemptive scheduler so that when you do, just comment yield doesn't mean anybody can see it. Only the programmer can see it. In the code, comment is taken out. It's just an infinite loop right there, right? So who does the yield? Well, there's no yield. This is not cooperative threading. If it's cooperative threading or cooperative multitasking, then yes, you have to call the explicit yield, kind of like how Python has it in the generator. But no, here, this means it's preemption. The operating system context switches this producer process out, then switches in the consumer, let it run for a while. right? So that's what's important here. The yield is only in the comment. There's no code for the yield, okay? So keep that in mind. That's how preemption works. So even though it looks like it's hogging the CPU entire time, OS grabs control back, gives it to the other process to run for a while. For how long? Until it fills up. Or a consumer would consume until it can't anymore. Or when the time slot is up, then it grabs control back, let the producer run for a while. So you see that they're not synchronized because of the buffer. One could be producing ahead and then gets context switched out, and then the other consumes. It's probably already some buffer length behind, right? So that's how that works. And can you really predict what's going on? Well, I mean, you could try, but most of the time, I mean, if your buffer is sufficiently large, you kind of have to just estimate and say, okay, I think it could be very different each time. So that's why I want you guys to try this for yourself. Change the parameters and then see how it behaves. Okay, make the buffer much larger or very small, and just to see, right? So this is a way for you to find out these answers for yourself. And different systems are going to behave differently. Okay, so this is the kind of thing I want you to try. Even though I'm not requiring you guys to turn in anything, you better try this kind of thing to find out things for yourself. And if you have questions, great. Try it on a program like this and run. Try it on different systems, on different buffer sizes, different whatever, right? And in fact, when you produce, it doesn't have to be something this simple. It could be much more complicated, or you could even have it sleep, or do it randomly. You have a random number generator and then have it do weird things. So anyway, so really, I think I just wanted to show you more worked out examples so that you can not just, okay, try it runs, okay, great. No, take it from there, do more on your own, right? Then try to answer your own questions. Really, that's the whole purpose, okay? And if you already understand this, you don't need to do this, fine. But really, you should try to use this as a way to find answers to your own questions. Okay. So that's the SHM example, both from the textbook and from the one that I showed. And of course, you need to understand static variables. And so one of the issues with static variables is what's called re-entrance. What does that mean? As we get into shared resources, especially threads, what's going to happen is you may have a same function that's called by different threads, right? Maybe one thread wants to call printf. Another thread, I want to call printf too, or maybe call one of my own function, one of my own functions, and then do something before calling printf, right? So they could do all sorts of things. So is that going to be okay? Well, depends. So that's what re-entrance means. A function that's re-entrant will be robust enough so that when you have multiple calls into it, whether from different threads or even recursion, it's going to be robust, and it's not going to be messed up just because there's one call and another call is still pending, hasn't returned. Because you can imagine making a call that's sufficiently long and it doesn't return yet, and then it gets context switched out. If there's a static variable like that, what happens? Then that is shared between the different threads, right? And is that okay? Maybe it's not, right? So, and we'll spend some time talking about race condition. That's called race condition, because you could be in the middle of doing an operation, A gets B plus C minus D. Before you assign to it, another instance comes in, and then it starts doing things. Is it using anything in common so that its results can be messed up? Right? So then maybe one does the update and overrides the other update by the time it returns. That's going to be bad, right? And so static variable means there is just one instance. And that doesn't mean having static variable automatically makes it not a re-entrant. You have to know what you're doing. But the fact that you have static variables, static locals, that is, means there's a risk. You better know what you're doing, okay? Because it's the same copy you're touching. And if you're depending on the assumption that there's only one copy active, then you may be in trouble, right? So we'll talk about this some more, but so that you're aware. Okay, and we saw generator. I mean, this should be simple enough, right? And pipes. Okay, if you want to work on pipes, you could. I mean, so here I think pipe code. I mean, using from the shell is probably the easiest because you just type one command. I mean, you all know how pipes work, right? So Unix pipe. ls, and then you can do ls and then sort. You can pipe it to sort, and you can pipe it to wc word count. Right, so you can do all sorts of things. What the standard out of one gets fed into standard in, which then takes it to standard out. But that's just one of the ways pipes can be used. That's how the shell constructs it. It takes a standard out, which is number 2 or 1. Standard error is 2. And in is 0, 1 is out. Yeah. Okay. So anyway, so it just hardwires the in and out, right? The out of one gets wired to the it's piped to the in of the other. But you actually can make more general pipes and construct crazy topology. But anyway, so that's that. And if you want to do it, okay, pipe. So I can do producer and consumer. CC pipe PC.C. Okay, so what does that code look like? So basically, to use it, you have to declare this array of 2. For 2 endpoints of the pipe, and then the PID, and this is again producer consumer, and then a lot of the same code you've seen, except now we are doing pipes, which is message passing, no longer shared memory. All right, and message passing means you do read-write calls as opposed to just directly working on the shared memory. Working on shared memory is a little risky because compilers really have less opportunities to do any checks for you. Okay, it thinks, oh, that looks like a local variable to me. It doesn't know somebody else could change on your behalf, right? Whereas read and write package things up. So okay, that's a read and that's right, and nothing else should happen while the call is proceeding. Right? At least that you can mostly make that assumption. Unless you declare something non-volatile, that's volatile. Anyway, so the syntax for reading and writing is read, you do the descriptor from the read end of the pipe and then put it into the buffer pointer. Write, you specify, just like when you do, remember, do fprintf, you put the file pointer, right, the file start, or if you do the lower level, you put the descriptor 0, 1, 2, and others. Here, we're not necessarily using standard in, standard out, so that's why it's the FD is basically filled in with the descriptor from the pipe call, right? And then the item you take from that or from this particular address, right? And we're just doing one at a time. And write, and then read, and so forth, right? So and then consume. Right? And so so the main program looks like this. Basically, you create a pipe by making the pipe call. Remember, FD is that array of 2 descriptors, right? And then if it returns -1, that means pipe creation failed. If it's successful, we do a fork. And then, yeah, I mean, just to be nice, we check if PID is negative. If negative, that means fork failed. Okay. But a lot of times I'm just lazy. I just check if it's greater than 0 or not equal to 0, right? 0 means child. Greater than 0 means that's the parent. I'm the parent process. I get the PID of the child process. Anyway, so whichever case, so depending on if you set one up as producer consumer, what happens? Well, remember when you do a fork, things get duplicated, right? In other words, the pipe, well, there was the pipe before the fork. But then as soon as I fork, what happens? You have 2 processes now, and that other one has another copy of the pipe too. But is that correct? Well, I just want one pipe. I don't want two pipes, right? So what needs to happen is, well, there's two processes, and each one is only supposed to use one endpoint of the process, not both, right? So that means if I do the one side, that's the producing side, then I better close the reading end, because the pipe has a writing end and reading end, right? So you better close as a producer, you close the reading end because you're just writing to it. As the consumer, or then you close the writing end because you're just reading from it, right? What if you don't do the close? Well, then you send something, and then it loops back to yourself as well, right? And that's not going to be good, right? So you better do the closing. That's why they're there, okay? And just close with a file descriptor, okay? It's in the same API as the pipe, open, read, write, right? So that's the only thing you got to watch out for. So once you know this, then yeah, that's fine. This doesn't do shared memory at all. This is interprocess communication by pipes. And pipes mainly work on the single machine. And a pipe can, in fact, be redirected to a file if you want to. Or take it from the keyboard, take it from different sources. And nicer thing, I think, is just it's a cleaner program because you're doing reading and writing as opposed to you get a generic pointer, declare some struct, and that struct had better be the same between producer and consumer. Here, it's reading, writing, call, and it does the synchrony for you. So that means you don't manage your own buffer. You don't have to worry about how big I want the buffer. The system decides. Okay, so the system, so even though I say I'm only reading, writing one item at a time, the system may have like 1K, 5K, 4K, 16K, however many K of buffer it thinks is appropriate. The system does that memory, buffer management, okay? So if you don't have to do buffer management, great. One less thing for you to worry about, because anytime you start having to manage your own memory, it's risky. Memory problems are pretty nasty, very hard to track, okay? And so here, you don't see any direct memory manipulation. All you do is, here is my buffer, I take it from this buffer, here's my buffer to write it into this buffer. That's what read and write will do. And then that way, it's fine, because you don't have to declare your buffer as a generic pointer. You can declare as any struct or any array or whatever. You already know what you're doing, okay? And so that way, it's safer. It looks safer to me anyway. I feel more comfortable doing this type of access compared to shared memory. Shared memory always makes me uneasy, and it's less modular. Here it's more modular, right? So anyway, so yeah, I think I'm kind of out of time, but there's additional code. So there's anyway, I have additional code, and so I think anything I posted in the Google Doc, please write, even though you're not required to turn anything in. Actually get your hands dirty, trying the code, not just compiling, running, but trying to make some changes. It's going to do you good. And even if it's buggy and you have to debug, you'll learn a lot from that process. Okay, so please do take the time, especially now. This 4-day holiday is coming up. What else are you going to do, right? So have some fun doing programming. Okay, so yeah. So then I'll have new material to cover next time. All right, see you next week.